Okay, welcome everyone. It's my pleasure as a professor here at EPITA to welcome you all to Scala I/O at EPITA. I hope we can repeat this again in the future sometime. So I'm a researcher at the EPITA Research Lab. In French is Laboratoire Recherche EPITA, I think. And I'm going to talk to you about some of the things that I've been doing over the past few years. The talk will proceed like this. I'm going to give a brief history of the project, very brief. And we're going to introduce regular type expressions, and I'm going to use the word RTE a lot. I'm going to introduce what that is by example rather than trying to give explicit definitions. And then in this project, I've identified 5 interesting challenges that I had to solve in some way. And we'll talk about those one by one, depending on how much time there is at the end, how much time we'll get into the efficiency. So, the history. So, I introduced regular type expressions at the 2016 European Lisp Conference. It was an implementation in Common Lisp, and it very heavily depended on built-in features of the Common Lisp language. And there's the citation of the paper. I went on to do a PhD thesis here at EPITA in the research lab. And basically that paper evolved into my PhD thesis. One of the pieces of feedback on the thesis was you should generalize this to other languages, not just Common Lisp. So over the past several years, I've re-implemented the idea in these 4 languages that you see here, and this is the first time that I've talked about it with regard to Scala. I've talked about it in some of the other languages. So the project was not to do the best implementation in Scala possible, but the idea was to implement something generic enough that conceptually would port to all of these languages. So some of the things won't be idiomatic. The idea is we want to efficiently recognize patterns, regular patterns, in heterogeneously typed sequences, and in Scala, this is represented by seq of any. Okay, so regular expressions by example. So let's take a look at this sequence, and there are some patterns in there, and you could imagine lots of different patterns, of course, but what's the pattern? It looks like there's a typo there that I just noticed, that there's a 2 that shouldn't be there. But anyway, so we have integers followed by some floats, and the floats might be doubles or single floats. And after each integer, there might be, well, in this example, 1 or more, and a question for the regular language is it 0 or more or 1 or more? How do we represent this in regular expression terms? So in regular expressions, we normally encode the information in strings. So the string has this DSL in there that represents how we want to match. And the domain we want to match from are strings of characters. So the meaning of this regular expression can be thought of it as this abstract syntax tree. You have a star operator on top of a concatenation operation, which breaks into an I for the character I, and then a plus for the 1 or more operator, and so on. And so we programs that do string regular expression manipulation have to convert this string somehow into this AST before they can continue. So how do we represent that in Scala, not trying to match characters, but trying to match types of objects, which might be characters or numbers or anything? So what I decided to do was, well, we'll talk about later exactly what we did, but this was the first challenge. How do we represent this surface syntax in a way that's meaningful in the Scala language? Okay, so let's look at an example. Normally in a regular expression, after you convert to the AST, you build a finite automaton. And then you traverse the finite automaton to figure out whether the sequence or the string is a member of the language of the regular expression. The language of the regular expression is a set of all strings that match the regular expression. So does this sequence match this pattern of int concatenated to either double one or more or string one or more, and then that entire sequence can be occurring one or more times. Okay? So how do we figure out whether that sequence matches that pattern? Well, we need to somehow build a finite automaton whose transitions are labeled by types rather than by characters in the normal regular expression idea. So the second challenge is how do we convert an RTE, a regular type expression, to a DFA, a deterministic finite automaton. And we'll talk in a few minutes about why deterministic rather than one of the many other types of finite automata that exist. Okay, assuming we have this finite automaton, we want to now make the decision, the predicate pattern, right? The pattern predicate. Does the sequence belong to the language of the regular expression? So we start in the initial state 0. We look at the first element of the string and we see that it's an integer, so we can follow the integer transition to state 2. If the first object is not an integer, then we fail. It does not match. So we can fail early. And then we see that we have a double, and we have another double, then we have an integer, so we come back to state 1, and then we have a string, we go to state 3, we have some more strings, integer, we come back, and we keep going, and we keep going. And at the end, when we reach the end of the traversal, we find that we're in a state, a so-called accepting state, labeled with a double circle. If we conclude the traversal and we're in like state 1, which doesn't have the double circle, then we don't match. If we're in an accepting state, then we do match, and we return true. Otherwise, we return false. So yes, it's a match. One thing that you might not have noticed, which I didn't notice the first time and was enlightening to me, we traversed the sequence exactly once. There is no backtracking. So we can match a regular expression in linear time regardless of the complexity of the regular expression. We could have a regular expression that fills many pages, but matching it against an incoming sequence is only a function of the length of the sequence, not a function of the complexity of the expression. And that's very important. But what if we have a finite automaton like this? We have a 2, so we advance to state 1, and then we have a 3, but 3 is an integer and also a number. So which branch do we take? Because integer is a subtype of number, and so those two types are not disjoint. So we could backtrack. We could go ahead and say, let's take the integer branch, and then 5.6f is not a string. Oops, let's backtrack and then take the number branch, and then we find that the next is a float, so we match. That would be one possible way, but the complexity then becomes exponential. It's a big difference between exponential and linear. So can we do something to convert this finite automaton into a deterministic finite automaton such that we always have exactly one branch in any possible case? And yes, we can. We can split the type into the types into integer and the type number and not integer. So those are disjoint types. 3 is an element of integer, but 3 is not an element of number and not integer. And then we have to make another modification in the state machine so that after we get an integer, we can still have a float. Okay. So it's not just that we have to split the types, but we may have to derive a different state machine in the end. And the important thing is that integer and number, the intersection is not empty. There are elements which are both integers and numbers. There are objects in your language which are both integers and numbers. So the third challenge is, how do we represent in Scala a type like integer and not number. Because Scala 2, which I was working in at the beginning and actually still am, doesn't support intersection types, and even Scala 3 doesn't support complement types as far as I know. The fourth challenge is then, given a set of types on transitions, how do we split those types into types that are not intersecting? Every type in the computed set is a subtype of exactly one element in the input set, and the unions are the same. How do you actually do this computation? Well, at all and then in an efficient way. And then finally, there's a question of efficiency, that this test is going to be something like an if-then-else. If X is in this type, then do something else, check whether X is in the other type. And as you see, we've already checked whether X is an integer, but here we have to check again whether X is a number and not integer. So can we avoid that duplicate type checking? And the answer is yes, we can. So in summary, we have these 5 challenges: how to represent the RTE at all in Scala, how to construct the DFA from the RTE, deterministic finite automaton, how do we represent a type lattice in Scala, so a type system which supports union, intersection, and complement types. How do we implement type partitioning so that we can ensure determinism? And then in the end, how do we eliminate duplicate type checks? The first challenge, how do we actually represent it all? We need some type of surface syntax which is declarative, expressive, and composable. We can build other patterns out of existing patterns. And we need a programmatic interface which is reflective, and we can do algebraic manipulation. So here's an example of what I came up with. We represent the expression as an AST, an abstract syntax tree. So we have internal nodes that represent operators, and then leaf nodes which interface us to the Scala type system. So we have this wrapper, this atomic wrapper that wraps a built-in type. And then we have these operators which we can concatenate, alternate, and repeat in various ways. And these, of course, are syntax sugar for other built-in operators with more interesting or uninteresting names. And the ADT, the algebraic data type for that set of types, looks something like this. We have operator objects, and we have some other objects which make the algebra complete, and then we have something that interfaces to the type system. And I can talk later if anybody's interested about why it's quasi and not a real ADT. The second is how do we do the construction? So there are a lot of techniques that exist for constructing finite automaton, some efficient, some easy. I had to adapt this to my work, which was a very interesting part of the development, and make sure that those finite automata are deterministic and not accidentally non-deterministic. So rather than explaining how that works, I'd just like to show an example of how the system is used. So I hope the font is big enough. Yes. So I have this sequence of any which is delimited by M's and C's. M stands for measurement, C stands for count. After an M, I have some measurements, which are numbers, could be doubles or floats. After a C, I have some counts, which are integers, which need to be positive. And then I can have as many of these M clauses or C clauses as I like in any order. So this is what I want to represent. So I can define an RTE, a pattern, to represent a singleton sequence of integers, DF to represent a singleton sequence of an object which is either a float or a double. If I have a predicate that maps any to Boolean, this one recognizes positive integers, then I can create a type RTE which is integer and satisfies the positive predicate. So this is a subclass of integer, or a subtype of integer. I have two types which are, I think Python calls these literal types. I don't know if that's standard, but the type that just contains the string m and the type that just contains the string c. And then I can construct my m and c clauses, m concatenated onto df.star and c concatenated onto ipods.star. Okay. Let's hope this works and doesn't have the demo effect. I don't know why it thinks it needs to compile again. Ah, good. All right. So we construct a pattern by combining the m clause, c clause with the dot star. Where is the next operator? There it is. And then we ask, does the data at the top, that's the m's and the c's and so on, is it contained in the language of the pattern? So this is basically matches. Does this sequence match this regular expression? I didn't use match because match is a keyword in Scala. I'd like to use that, but so it contains. Okay. So we see that yes, M1 does match. We see the editor there displaying the value of M1. We can take a look at the finite automaton. So we see that we have an initial state, which is also a final state in this case because the empty sequence happens to match the expression. We have two interesting types, T0 and T1, which are M and C. So if I have a T0 or T3, I go to a different part of the state machine to recognize something different. T0, I then need to recognize T1, which is a double or float in this loop. And T3s, I have to recognize T2, which is integer, which is positive, ipods question. It's just how it's printed out in the print object method. And then, okay, so that's the how the state machine looks. But what about this pattern? So pattern 2, which is m concatenated onto df dot star and c concatenated onto I dot star. Is that the same expression? Does it match the same set of sequences? Which is quite often a problem in regular expression design. You want to optimize a regular expression and you don't know, do I now fail to match something that I used to care about matching? Okay, so again, I still match the data. Okay, so it looks right, but well, let's take a look at the finite automaton to see if we see a difference. So it looks the same, but you notice here we have type 3 as an integer, and in the old one we have type 3, it's an integer which is positive. Oh, so we're not distinguished positive. Our new pattern forgets to distinguish about positiveness. Okay. Suppose that you don't want to look at a huge finite automaton. Why don't we construct the pattern that's the exclusive OR of the original patterns? So give me the set of all sequences which match pattern 1 but not 2, or pattern 2 but not 1. Basically matches one or the other but not both. So let's see, construct a finite automaton. I think it's slower if I don't plug it into power. Okay, so quite a bit uglier or more beautiful depending on how much you love looking at a finite automaton. I think my chef is probably really liking this. But okay, so this is the state machine that matches all sequences that either match pattern 1 and not pattern 2, or pattern 2 and not pattern 1. So what's an example of a sequence that's in this class in this language? Well, we could start at state 1 and trace the arrows to any final state. You could do that in many different ways, right? You could do this, and then this, and then this, and then this, and then that. Okay, that would be an inefficient way. What you'd like to do is maybe find the shortest path. So some sort of Dijkstra search that finds the shortest path through the finite automaton. And that's exactly what this spanning trace does. So the list of types that would have to be on objects in order for this pattern to match, well, the trace is sum of right of list. So sum means yes, I found a candidate rather than none. Right meaning this is a satisfiable set of constraints. We'll talk about when that's not the case. And then so an object of type equals C, so the C string, followed by an object which is both integer and not positive. Okay, and then I can go, okay, well, that's nice. Give me an example of such an object. So it finds the object who is, well, it found an object, so sum, list of some C and some 0. So there is the case that I know the type, but I can't find an object of that type. In that case, you would have a none in there. Okay, the type says it's possible, but I don't know if there's an object actually in that type. Okay. Good. Where is my presentation? There it is. Okay, so we have a representation of the regular type expressions. We have a way to build a finite automata, and we have some methods for manipulating finite automata and doing things like XOR and finding paths through the automata. How do we actually support these Boolean combinations of built-in types? So we need to support what's called a type lattice. In this case, it's a type complemented lattice because we have to support not only and or, but also not. We want to embed this into the programming language. So I had the task of embedding this into Scala, but also into Python and into Clojure. And it was built into Common Lisp, so I didn't have to implement that. And I need to at least be able to do type membership checks, given an object, is it an element of the type? And answer subtype questions. Is one type a subtype of another type? I need to do that because I need to compute type vacuity. So if the intersection is a subtype of the empty type, that means the types don't intersect. So again, we can represent that we have OR nodes, and not nodes, and at the leaf levels we have either interfaces to the Scala type system or the special, what did I call them, literal types. We also have this satisfies type and maybe a few other types for the algebra to work. Here again is what the abstract data type looks like. So the combinational objects and then the terminal objects and then interface to the Scala system, or in the Python code there's an interface to the Python type system there. Here's an example. It looks a lot like the RTE code, but is subtly different. I can ask, is minus 42 an element of the integer type? Okay, that's easy. Is 7 an element of the type, which is the union of the string type and the integer type? And yes, it is. And then I have a predicate which detects oddness. And then I can ask, is 36 a member of the satisfies odd p type? Okay, that's easy. The subtype predicate is more complicated and much more interesting. So if I define these types again, string, integer, number, and odd, and I want to ask, is string a subtype of integer? Well, no, it's not. But why some false? Is integer a subtype of number? Yes, it is. is odd a subtype of integer? So how could the system know when I've written this predicate function whether odd is a subtype of integer? So in this case, it returns none. I can't prove it's a subtype, and I can't prove it's not a subtype. Okay? So I have to make my system robust, even in the case when the subtype relation is uncomputable. This uncomputability can happen for many reasons. The most obvious case is the satisfies predicate. Those become undecidable very quickly. Code that determines subtypeness of very complicated Boolean expressions. The code can be very large, and to make it correct, it has to be very inefficient. So some very complicated expressions, you have to simplify them before you can ask subtype questions. And so in that case, it might return don't know. So yes, no, or don't know. Another problem is on JVMs greater than 8, there's no dependable way to find the subtypes. If somebody is a Java expert and says you're wrong and wants to show me, I'd be very happy, because then I can move my code from Java 8 to something more this millennium.
Question.
Yes?
That means in Java 7 you can do it?
I don't know how the odd numbers from one sequence and the even numbers from another sequence. You can't do it in Java 11 or 14. I can talk about that. But yes?
JVM greater than 8. What happens?
What happens, you ask for the subtypes and it tells you there are none.
No, but are you implying that before Java 8 you can do it in Java?
Yes, exactly.
Why? So I think
because the library works. The library, I have a slide on this. I can explain it now and then go quickly later. But there's a open source library that opens up the project and looks in the jar files and finds all of the this and that. And the jar file format has subtly changed at some point, and this code no longer parses it, or no longer dependably parses it. And that particular code is no longer maintained. So some Java expert could probably fix the 1 or 2 lines in that code and make it work again. You know, the first character is a comment instead of a piece of code. Maybe it's something very simple like that in the code that just could be fixed. I'm very happy to claim that I've been programming since 1981, and I've never written a single line of Java code, and I would like to finish my career with that gold medal. And it gets harder and harder because things like this I want to go and fix, but out of principle I don't. So where are we? We have, what have we done? We have wrapped the Scala type system with a new type system, which is a runtime reflective type system. I call it simple because it doesn't do a lot of things intentionally that a very powerful type system does. It's simple so I can do the type algebra I need to do. Basically, and, or, and not. Complemented type lattice. I can always answer the membership question, and the subtype question I call a semi-Boolean predicate. It returns yes, no, or don't know. But when it returns yes or no, you can depend on the answer. The Scala built-in subtype question is A a subtype of B? It's can I prove A is a subtype of B? So it conflates not a subtype with don't know. Okay, deterministic. Okay, we're good on time, I think. How do we partition a set of type I call them type designators. They're objects that represent types, objects that designate types. How do we do this construction or this deconstruction even when the subtype predicate is unknown? And that's what makes the problem interesting, of course. Okay, we looked at this already. Integers, a number have an intersection. So I basically consider 4 types: not integer, not number, integer and number, integer and not number, not integer and not number. But I know that integer and not number is empty because integer is a subtype of number. So that transition I can remove, and the state, the useless state, I can remove because I can prove the type is empty. If I have a case like int and odd, well, I can do the same decomposition, and we know that odd and not integer is empty. We know because we're human beings, but the machine can't decide that because it can't look inside the odd function and figure out how it works. So we have an unsatisfiable transition, but we cannot remove the useless state. It's worse than that because in the case that we can determine the type is empty, we can remove the state, but we can remove all states that depend on that. So it could be that a large portion of the state machine is obviated. And of course, in the type of integer and odd, that's no longer the case. These states are unreachable, but I can't compute the fact that they're unreachable. There are plenty of cases that I can determine type intersection voidness. So if I have two classes which are final classes, then there is no common subclass. There's no object which is both type A and type B because they're final. However, in the case of C and D, I don't know. I have a type C and a type D, which is this trait, but I don't know whether some subtype inherits from both of them or not. And in the case here, I know that E is a subtype of G, that G is a subtype of E, so therefore the intersection is not empty. And those types of that information I can ask the Scala system because I have the objects. But if I want to ask, are there any subtypes, I can't answer that question. Well, I can't answer that question after Java 8. Well, here's the library that's no longer maintained. So when you ask, how do I find the subtypes on Stack Exchange, they say, oh, use this library. And then you look at the library and it doesn't actually work in a dependable way. Okay. The final challenge was how do we do these type checks in a efficient way? So if you can imagine, we have some object, some variable x, which has the value that it got out of a sequence that is iterating over, and we need to either decide whether to go to state 1, 2, or 3, depending on these three types. So whatever you do there is more or less equivalent to if x is a member of this type, then 1, else if x is a member of this type, then 2, else if x is a member of this type, then 3, else maybe fail because it might not be exhaustive. Okay, so the code looks something like this. So to make it fit on the slide, I'm abbreviating number and integer just by n and I. So if n and not I dot type p of x, then return sum 1, check this type, then return sum 2, and else sum 3, otherwise none. So none will get returned in the case that this is not exhaustive. But of course, as you see, I'm checking n and I, and then I'm checking I again, and then I'm checking n again. So certainly this can be optimized. Once I've checked n, I don't need to check it again, ideally. So because this data structure is machine generated, I'm not really manipulating if then else, right? I'm manipulating a data structure, an if then else data structure, which just has the types and then the alternate or the consequent and the alternate in there. But for the purpose of presenting this, the simplifications that are going to happen deal with these data structures. But I'm going to show that using the if then else because I think that's a bit more readable. So first thing I do is I choose one of the types, maybe the first type that I encounter, and I duplicate the code around if X is in the type and else. So the same code duplication in both cases. Okay, move that to the left, and let's apply the next. So now, in the then part, I replace all supertypes of n with S top, which is the top type, the universal type, and I replace every subtype of n in the else part with the empty type. So n is replaced with S top, n is replaced with S top, n and I are replaced with S empty because integer is a subtype of number. Okay. And then, this is the same thing, right? And then I can do some algebraic reduction. The universal type and X is X. The negative or the not the top type is the bottom type as empty, and several algebraic simplifications, so I can apply those. Next, is X a element of the empty type? No, it's empty. So every occurrence of this I can replace with false. And is X an element of the top type, the universal type? Yes. So I can replace that check with true. Move that again to the left. And now I can replace if true else X, if true then X F. I'm speaking too fast. If true X else Y with X. And if false X else Y with Y. So then most of the code goes away now. Because we have if true this else none. Right? And so a lot of that goes away. And then I can do the same thing with the next type. In this case, there's just two, n and I. So I go through that. I introduce the duplication if an element is in the type or not in the type. I replace the supertypes of I with the top type, the subtypes of I with the bottom type, the empty type. I do the algebraic reductions. And is X an element of the empty type? Is X an element of the top type? I replace those with constant trues and falses. And then I do the if then else reduction. And I get that. So if X is a number, then now check if it's an integer. If it's not a number, just return some. If it is a number, well, if it's not a number, we don't have to check if it's an integer, right? So that part has gone away completely. Then if it is an integer, return some, else return, well, some 2, some 1. And another thing you'll notice is there's no way for it to return none. So the types are exhaustive. Okay. So that code got reduced to that. So the 4 challenges, I think I've talked about a little bit, how to represent these regular type expressions in Scala. How to construct the DFAs. Okay, I didn't tell you how to construct them. I'm happy to talk about that as much as you like, one-on-one. Embedding the type system in Scala. That's potentially a controversial item. And during this project, every time I asked on Scala sites, how do I do this and this and this? The answer is always, you shouldn't be doing that. Okay. Why do you want to do that? Okay, I refer them to my PhD thesis, and they say, and they usually don't answer after that. Determinism and efficiency, we talked about a little bit as well. So in summary, what do we have? So regular type expressions in Scala, they're using a technology called symbolic finite automata, which these types of automata that have labels rather than letters on their transitions. Extending the Scala type system to do something that it probably was not intended to do, and sometimes I have to really, really force it to do the thing that I want it to do. We saw the demo. I'm happy to answer questions about that. And some of the parts that I thought were quite theoretically interesting. Several things we can do remaining. I talked about finding a replacement for this abandoned library. I would like to move away from Scala 2, but I'm afraid because I'm doing a lot of stuff that I don't understand, because I asked people how to do this and copied the code, especially with these implicit this and that's. So it works, but I don't know why it works. I just copied the code and I hope I put a reference there to the person. I have this idea of open and closed worldviews, the idea that the types that exist now may not be the same ones that exist 5 minutes from now because Java might load a new library. So I have this idea of a closed worldview, assume that no new types come into existence. Yes, okay. So with that, I'm happy to answer any questions, complaints, objections. Yes, sir.
Question. So with regards to this open world, isn't it then hopeless to try to find that library replacement for it? Because if I understood you well, you were looking for all subtypes of a type. If you have an open world, it's hopeless.
As I understand, this library searches your project and all of the libraries that you could load.
Okay, and you don't care about a subtype of a class that you load, but you don't load that subtype ever, so you're not worrying about that.
Well, if I know about that type, then I can account for it in the code. But if you know you're not going to load the type, okay, so I'm putting the responsibility on you when I really should have a responsibility myself, right? So I can use this closed worldview, and then I don't care about this possibility. So the results are undefined if you load types after it has already cached some of these finite state machines. Yes, sir.
Question, thanks a lot for that. Super interesting. I see you use a XOR between the two patterns you showed, meaning you cache you match with the first pattern but not with the second or the other way around.
Yeah, the XOR type.
I figured that your second pattern was including all the patterns that are matched with the first one.
Okay, so you want to ask, is one type a subtype of the other?
Is it something that can be checked?
Yes. So that's one of the operations within finite automata. You can ask, is one language completely included in the other? And what you do is you say, one language and not the other, is that empty or not?
Yeah, it's actually a part of the XOR.
Yeah, it's part of the algebra, yes.
Okay. Why using the XOR and not this operator, example?
I thought XOR was sexier.
Thank you.
Okay. Question, Uli?
No.
Yes, sir.
Another one, if I may, does this extend to composite types like tuples? And I would assume the theory does, but then
Yeah.
whether your library
No, okay.
does.
If I understand the question of tuple types, so I explicitly don't define tuple types in, it's called sets, simple embedded type system. So it models types as sets. And I explicitly don't model tuples in there. My idea is if your type system has tuples, which Scala does, but which Pythons and Common Lisp do not, then you can still use that by an atomic type of tuple. But you have a problem of recursion, right? Because you want this system to be like composable.
But you want a tuple of foo and bar, but in the runtime, the Java runtime is going to be the same class for.
So if you want a tuple of integer, of positive integer, comma, double or float, okay, currently I don't support that. It could be supported, but then it wouldn't be compatible with Python and the other implementations. So if somebody finds a really good use for the code, it's a trivial thing to add, but it would then break, theoretical compatibility. Yes, sir.
What kind of real world usages do you see on
So,
this?
so this is an excellent question. The question is, why? All right. So one reason of presenting this talk is to find out, is these useful for something? So for me, it's interesting theoretically, because I want to extend regular expressions into type checking, and especially for untyped languages. Like when you have a large data structure and you really want to check, my code is going to do this operation to it, and if I can check it efficiently once, I can remove all my type checking out of the traversal code. So maybe in Scala, when you're reading unsafe data, like JSON or whatever, you might want to efficiently check if the data is in a certain format before you pull it into your code that expects it to be in the right format. Maybe that's useless because maybe there are better ways of doing that in those libraries, like JSON libraries and such. Anyway, I don't know. I don't know if that answers your question. But my main purpose was theoretical interest.
Thank you.
Okay. Well, thanks everyone for listening. It was a pleasure.